derivatives of logarithmic functions. You totally know that you want to be able to take them to compute them correctly. So let's work on some practice right now. Let's start by reminding ourselves of the basic rules for derivatives of logarithmic functions. We want to take ddx of natural log of x. We get 1 over x. And dx of log base b of x is equal to 1 over natural log of b times 1 over x. If you look up tables of tables of derivatives, then you probably will find in the table that they put absolute values right here. And that's so that you can actually evaluate the function at negative values, because natural log is not defined for negative inputs. So by putting absolute values right here, you can evaluate it, and then you recover 1 over x, which is really cool. I find it's a bit cumbersome to put the absolute values in everywhere, and so I kind of get sloppy, and I don't always write them. Of course, these are the basic rules for doing derivatives of logarithmic functions. But we've been working on our composition with our composition rule, or the chain rule, for quite a while now. And we want to be able to put more complicated things instead of x right here. So here's the general rule for what you do. You go dx of natural log of f of x, absolute value, is equal to 1 over f of x, 1 over x, right? Because instead of x, we have f, times f prime of x. And then you'll often see it written that they're going to take and put this f prime on top of this thing right here because it's multiplying by 1. And so you'll see this written as f prime of x over f of x. So if you ever see a function on the bottom and its derivative on top, it probably came from differentiating a natural logarithm function. Okay. I think it's really important to keep reminding you about the chain rule because it is so super important. So let's do a derivative of a natural logarithm function that has a more complicated thing in its argument. So how about let's take f equals the natural log of x squared plus 2x. Now I want to take the derivative of this thing. So we're going to write down what f prime is equal to. See a natural log on the outside. That's the dominant feature of this function, is natural log. The derivative of natural log is 1 over whatever the argument was. It's 1 over whatever the argument was. So the derivative of natural log is 1 over, and then I put this thing right here, x squared plus 2x. Formally speaking, it's 1 over x squared plus 2x, and then I'm going to chain out the derivative of the inside. So now I've got the inside function. We already did the logarithm. So now I've got to multiply by the derivative of the inside, and that's 2x plus 2. And then it might be nice to not have that dangling because it looks a little misshapen. So we might go 2x plus 2 over x squared plus 2x. And that's what f prime would be equal to. Why do I have too many equals? Okay. Let's wipe and do another problem. So for this next one here, let's mix up and do a little bit of product inside of it or something like that, right? We can always make these kind of arbitrarily complicated, and at some point it becomes like too much. So let's do one that has some like log base b in it, because that sounds fun. And let's require the chain rule with some like power rule stuff. So how about let's take let's take log base 3 of cosine of x, and let's take that to the third power. Let's make that not be 3 so that we don't, just because I'm teaching right now, I'm not particularly afraid of it being 3, but I don't want you to like get mixed up on which 3 came from which place. So let's call that good like that. Okay. So when I approach functions and I'm going to take the derivatives of them, I'm going to look at the function. I'm going to be like, well, when I stand back and blur my eyes, what do I see? I see something to the fourth. I see something to the fourth. And the derivative of something to the fourth is 4 times something to the 3. So f prime is equal to 4 times natural, nope, that's log base 3. 4 times log base 3 of cosine of x to the third. Okay, so we dealt with the to the fourth power, so now we've got to deal with the stuff on the inside. The stuff inside is log base 3 of. Log base 3 of. The derivative of log base 3 of is 1 over natural log of b times 1 over whatever was inside. So times 1 over natural log of 3, and then we like to moosh those together also. And then I'm going to take the inside and put it there, cosine of x, because that's what was inside the log base 3. And now we've got to chain out the derivative of the inside of that log. And the derivative of cosine is minus sine. And it's multiplicative, and so I'm going to put it right here. Rather than put it trailing and then move it on top later, I'm just going to put it on top right now. And there really isn't any simplification available to me. Excuse me. I guess I could write sine over cosine as tangent. Is that a simplification? I don't think so. Maybe I could move that minus sign out to the front there. I'm not sure that really makes it any better for me either. It does kind of look like I'm subtracting right now, so maybe I am going to put that out front to indicate that I'm not subtracting sine x over log 3 cosine x. It's negating the whole thing. Yeah. So that was 2 examples of derivatives of logarithmic functions. And I think maybe I'll just do a quick one that involves just basic log again. And let's mix in some other functions as well. If you feel like you got what you needed out of this video, by all means, move on with your day. I would love to have you continue on with me, however. Okay. Let's take x squared plus 5x times natural log of x as our function. Let's compute f prime, not f to the 1, but f prime. I see product. 2x plus 5 times natural log of x. Careful on those parens, my friends. Careful on those parens. Plus x squared plus 5x times natural log of x times 1 over x. Careful on those parens. And let's see here. So I could cancel. Some 1 over x. I'm into that. Equals 2x plus 5 times natural log of x plus x plus 5. Yeah, and I think that's probably about as simple as we're going to get. Yeah, I don't think that's getting any simpler. Okie dokie. Thank you very much for your time. I appreciate you, and I hope that you have a really good one. Bye.